Hello viewers, in today's class we are going to discuss a very important topic from binomial theorem, right? So here we have to solve a problem in which we have to find the remainder when 8 raised to 2n minus 62 raised to 2n plus 1 plus 3 is divided by 9, right? So here what we will do will make use of an important concept from binomial theorem. So let us first see the concept and then we'll see how we can apply the concept to these type of problems. So let us first consider the expression that is 1 plus x raised to n, right? Where n is some positive integer, and if we expand this binomial, then we can write the expression using the binomial theorem, right? But here to solve these type of problems, what we do, we write 1 plus x raised to n as 1 plus x times lambda, where lambda is some positive integer. So here we are not going into the detail of this result, but here we are going to directly use this result. So 1 plus x raised to n is equal to 1 plus x times lambda, where lambda is some positive integer and n is also some positive integer. And similarly, if we have say x minus 1 raised to n, then x minus 1 raised to n can be written as 1 plus x lambda, where again lambda is some positive integer, but here this exponent n should be an even positive integer, right? And when this n is an odd integer, then we have x minus 1 raised to n is equal to 1 minus 1 plus x lambda. And again, lambda is some positive integer and n is an odd integer. So now let us see how we can apply these results to this problem. So let us first take this expression as y. So y can be taken as 8 raised to 2n minus 62 raised to 2n plus 1, and here we have plus 3, and remember this n is a positive integer, right? So let us first see this term, that is 8. So here we have 8. 8 can be written as 9 minus 1. And then let us take this term 62, which can be written as 63 minus 1. Right? So we have now y is equal to 9 minus 1 raised to 2n. Then we have 63 minus 1 raised to 2n plus 1 plus 3. Right? Okay, now let us check the exponents. Now here we have 2n, and 2n is a multiple of 2, so 2n is an even positive integer, right? And here we have 2n plus 1. So 2n plus 1 is an odd positive integer. So now let us apply these rules to these two terms. So here we have 9 minus 1. So here we have x minus 1 raised to 2n, and this exponent is here even because 2n is even positive integer. So 9 minus 1 raised to 2n can be written as 1 plus x lambda, where x is 9. So we can write 9 minus 1 raised to 2n as 1 plus 9 lambda, where lambda is some positive integer. Now let us consider this term. So here we have 63 minus 1. So here 2n plus 1 is an odd positive integer. So we'll consider this case. So we have x minus 1 raised to n is equal to minus 1 plus x times lambda, where n is odd. So 2n plus 1 is odd. So we can now apply this result to this term. So we have here a minus 1 plus x lambda. So here x is 63, and since we have already considered the integer lambda here, so here we can introduce a new positive integer, say mu. So 63 minus 1 raised to 2n plus 1 can be written as minus 1 plus 63 times mu, and here we have 3. So let us now simplify this expression. So we have 1 plus 9 lambda, here we have minus minus plus, and then we have 63 minus 63 mu plus 3. So let us collect these two terms. Here we have 9 lambda minus 63 mu, and here we have 1 plus 1, 2, 2 plus 3, that is 5, right? Now let us take 9 common from these two terms. So we have 9 here, then we have lambda, then here we have 9, 7, 63. So this is 7 mu, and here we have 5, right? Now see, lambda minus 7 mu may also be written as some new integer, say m. So we can now write it as 9 times m plus 5. So now we can conclude that y is equal to 9m plus 5, where m is some positive integer, right? And from this expression, we can see that when y is divided by 9, then the remainder is 5, right? So the remainder is equal to 5.